Yes. Okay, so yes, topic is the squish map. So I guess I'll leave the title slide up here for a second. Do you want to like sit down or? It's totally fine. So yeah, so this the topic is about perfect matchings on the hexagon graph, which I think I'm probably not even the first person to talk about that now. I've just arrived, so I'm not quite sure what first and second talks were about, but guessing one of them was probably sort of about this. I'm not sure if that's actually correct or not. So what we're going to do is we're going to take the regular hexagonal, honeycomb graph, and then sort of every other hexagon, we're going to identify as special. We're going to put a star in it. I guess one hexagon out of 4, really. So leaving sort of a ring of hexagons around each. And then what we're going to do is we're going to make those hexagons bigger. We're just going to draw them bigger. This is just a redrawing of the graph, so there's no change here. And then bigger still. Eventually what you see is you see a coarser copy of the regular hexagonal lattice here. The purpose of redrawing it this way is to be suggestive. So we are going to take a perfect matching on this. When drawn as a perfect matching on this, some of the edges are going to become invisible. They're going to shrink down into little things, little very short edges, and then we'll see some other configuration on this graph here. The idea is to understand the relationship between the two. I'll draw a picture of this here. So. All right, so there is a perfect matching on the honeycomb graph. I've just sort of drawn one at random or arbitrarily. Oh, and I forgot to even say my co-author is Leigh Foster, who is a member here for a longer portion of the program. So you can discuss this with Leigh even after I've left this conference. Okay. So, yeah.
You are not Benjamin Young, or are you?
Wait, I'm totally am. No, I mean this one is me. Okay. Are there other questions? This is like hardest question I've ever been asked. Right? Yeah. I want to ask a follow-up question, but I don't even know where to start. Okay, so we're redrawing this perfect matching here. So we do this once with this slightly reconfigured graph there. And then again here, going from here to here, it's a little bit difficult to see what has happened, so I actually removed the graph itself that is underlying it. It just left the perfect matchings edges here. So what do we have? So we have this, basically, we have a number of doubled edges. Let's see if my highlighter actually, yeah, this works. So we have a number of sort of doubled edges like that. And then everything that remains is, it looks like, is going to be some kind of collection of closed loops like this. So if you've been in this game for a little while, you see that you have a collection of doubled edges. So they really are there with a multiplicity too, right? This edge, maybe a little bit easier to see up here, this edge and this edge are both present. Whereas in the closed loops, they're all single, right? This one, this one, this one, this one. So this is a configuration with degree 2 everywhere. Yeah? When you have one of those, a perfect matching is like configuration with degree 1 everywhere. So this is really just 2 perfect matchings superimposed. We call this double dimer model for the obvious reason. So when you take one of these single dimer configurations and run it through this squishing procedure, it shows you how to get a double dimer configuration on a bigger version of the hexagon graph. The talk is an exploration of this idea. So I came up with this idea, just what I've shown you so far, maybe like quite a long time ago actually, as a sort of a failed attempt to finish my own PhD thesis. I finished my PhD thesis another way, but since that time, you know, the question remains, like, if you start with a known measure, a probability measure on single dimer configurations, on perfect matchings, what sort of measure on double dimer configurations are you going to get after you push it through this squish map? And the technology to answer that kind of didn't exist until substantially after I graduated. So it is a sort of an interesting probability measure on double dimer configurations, and it indeed is an instance of one that Rick Kenyon worked out. He has this SL2C double dimer model, and I'll explain a little bit about what that is.
Is it clear that you don't get vertices with degree 0?
It is sort of clear. Yeah, so right, like maybe in order to show you why this always happens, or why you don't get other degrees as well, I'll need a slightly bigger picture than the one I've drawn. So just ask me again when you see a bigger version of this and I can point it. Thanks, Arvid. So the problems I like best are about plane partition enumeration. So it is good to think about the boxed plane partitions. So again, I'm assuming that if you haven't seen this picture yet, you're about to see it again. There is this bijection between perfect matchings on this hexagon graph and tilings of this hexagon here. The bijection is passed to the dual graph. When you have one of these edges present, it is joining a primal vertex to another primal vertex of the opposite color. In the dual graph, that is the same as sewing together the two triangles in the dual graph cell. That makes a tile. So perfect matchings, same as tilings. And by sort of like looking at what I've drawn, you could imagine that this is an empty room in which I could pile cubes. So yeah, I guess this isn't a touchscreen, is it? I have to go over to this. So for instance, here is another configuration, another perfect matching. It is, now it looks like a 2 by 2 by 2 stack of these unit cubes. And then there are a number of others. There are 18 others, in fact. There's 20 of these box plane partitions in a 2 by 2 by 2 cube. Here's one that's got 3 cubes, 1, 2, 3, just there. So if you look at what happens to them under the squish map, this top one, so all 4 of these edges here, so 1, 2, 3, 4, those edges, 2 of them go to here and here. These 2 here on the corner and then the center, and then the ones, these ones become very short. It just of the way the parity of the lattice happens to land, and so what you end up with, this whole region collapses down to these 2 matched edges there, and then the rest of it, you get this. So this one under the squish map goes 1-to-1 onto this unique thing here. It's just 2 copies of the empty boxed 1 by 1 by 1 plane partition. No box, and then another thing with no box. The super full one with all 8 cubes there goes to 2 copies of the full 1 by 1 by 1 box plane partition. Just there's a box there. Like you can maybe see the box if I draw it on. Something like that. And then literally everything else, all 18 others, go to this configuration here. And it's, it's not completely clear why yet, but we'll see why in a sec. What I will tell you is that this situation, well, sort of see why in a sec. Well, I'll tell you that this situation is representative. So here's what happens in general. So if I've got a plane partition, I want to think about it as in terms of its like 3D Young diagram, like it's made of unit cubes. And what I want to do is I want to approximate it with 2 other plane partitions, which I'm just going to temporarily call pi min and pi max. There's some chance that that's what we called it in the paper. I don't think I checked that when I was writing these slides. Anyway, what you want to kind of do is take the plane partition pi and approximate it with 2 by 2 by 2 cubes, like big cubes. This is like building something out of Lego and then trying to build the same thing out of Duplo, right? There's two things you could do. You can kind of round down, like whenever I don't have a full 2 by 2 by 2 cube, I take that stuff out. When I do that, I get pi min here. It's just a one big 2 by 2 by 2 cube coming from this junk in the corner here. Or I could round up. Whenever I have a partially full 2 by 2 by 2 cube, I fill it in, and I get this other thing called pi max. Okay? Once I do that, each one of these comes with a dimer configuration here. I've, just for the purpose of seeing it as a tiling of something, I've enlarged this room to be, I guess, 1 by 2 by 2 or whatever. Fill it in with the perfect matched edges. So that's pi min's dimer configuration. Here's pi max's dimer configuration. And then just put those together. So just this and this, draw them in the same graph, and then you get this picture. So that's what the squish map is actually doing. So this is, if you think this is like a slightly fancier version of what I had in the last slide, right? When I had the empty configuration, it went to 2 copies of the empty configuration. Full configuration went to 2 copies of the full. Everything in between went to an empty and a full. The empty one was over here and the full one was over here. When I round down, there's no box. When I round up, there's a box. Put the empty configuration on top of the full configuration, you get this loop, this one hexagon loop. So is it clear? So this is what it's doing on the level of plane partitions. I think this is like what the first thing that we worked out. Okay? Great. So, still not clear why we're doing any of this. I mean, ultimately, we're doing this because it's a cool thing we noticed and we wanted to kind of explore what we could do with it. I mean, I think that's the real answer here, but that's not a really great motivation research. Why you can't write that on grant, right? So you have to, we'll try and give a slightly better motivation later. So now let's address, or at least start to address, the question of which probability measures can arise on the double dimer model when you push through known probability measures on the single dimer model. Okay, so let's first of all, this isn't the most natural one, as you'll see why in a sec, but let's think about the one we understand best first, say just the uniform probability measure, say on the box 2 by 2 by 2 plane partitions. I just said there were 20 of these things. So that tells you what the probabilities are of getting these configurations here. You learned that the probability of this is 1/20th, the probability of this is 1/20th, and everything else gets collapsed onto this, all 18 other configurations get collapsed onto this picture. So the question is, what is this probability measure, right? It's not, yeah, the first thing that you think of is, well, maybe it's just 2 copies of like 2 independent single dimer models. If you have 2 independent single dimer models on the same graph and superimpose them, you get a probability measure on the double dimer model, but it's sort of trivial, and that's what we will call it. This can be represented as a trivial double dimer model. Perhaps unsurprisingly, you just sort of make it, you just have to have 2 different probability measures on the 2 copies of the single dimer model that you put together. Maybe you have one of them prefer to have a box and one of them prefer not to have a box. And then you work out sort of, what's the weight of that thing, and it's just some really annoying number. It's got like square root of 5 in it or something like this. So this technically could be, this one, realized as a trivial double dimer model, but not in the obvious way, not with the probability 1/2 or something. Like really the weight should be like, a quarter, a half, and a quarter, for instance, if you had 2 uniform measures on the single dimer model there. But if you try to squish anything that's even the only reason that this is possible to realize at all as a trivial double dimer model is that this is such a small example. If you try and squish anything larger, you get a quite non-trivial double dimer configuration. It's not just 2 independent copies of a single dimer configuration. So I would say the main theorem from our paper is that what you get is an instance of this SL2C double dimer model of Rick Kenyons. So it is now time for me to talk a little bit about these single and double dimer models. Let me very briefly remind you how the single dimer model works. So these ideas go back to Castellan from 1961. So the idea is whenever you've got a graph that's planar and bipartite, and you have weights on the edges, then there is a matrix. The matrix is called K for Castellan. It's basically a variant of the adjacency matrix. There's a way to put signs in the matrix in such a way that when you take its determinant, normally the determinant is going to be a product over certain permutations. In this matrix, the rows are indexed by the black, this is bipartite graph. So rows are indexed by the black vertices, columns indexed by the white vertices. When you take the determinant, it's going to be a product over permutations that sort of, if you like, pairings of black vertices to white vertices in the graph. So those are going to be perfect matchings. Each one's going to come with a sign. And there is a way of putting signs on the edges to cancel all the other signs out so that when you take the determinant of this matrix, it counts the perfect matchings of the graph. Moreover, there is all this work, very familiar to everyone in the audience. I'm going to attribute it to Rick, I think. But this idea that if you invert the Castellan matrix, the entries and also the minors of K inverse are going to carry information about the probabilities that different edges appear in the graph.
No, this is very... Michael Fisher knew this.
Oh, Fisher knew this, okay. Fisher, okay. So wait, so what's the actual story? So Fisher knew that the...
So Fisher has a follow-up paper with his student Stephenson, I think, where he computes correlations on Z2.
Aha, okay. No, I did not know this. I'll have to talk with you about that on it. Yeah. In which case that would substantially predate Rick's observation. Yeah, so I mean, maybe an easy way to say it, if you were just interested in one-point functions, like the probability that a certain edge is present in a randomly chosen perfect matching, this is kind of given to you by Kramer's rule for the inverse, right? Kramer's rule says that to take the inverse of a matrix, you strike out a row, you want to know what the entry is here, you strike out the corresponding row and column, and then divide it by the matrix. Well, that's a probability, right? This is striking out a row and a column in this matrix is like requiring that edge be present in a perfect matching. And then the thing downstairs, you still have to check that what you get is a Castellan matrix. It's counting perfect matching. So in any event, it's just counting the probability that there's that edge in the perfect matching. Similarly, minors of K inverse are going to compute other correlation functions, the probabilities that your favorite 2 edges are there, favorite 3 edges, etc. Moreover, if my graph G and the weight function are particularly nice, this isn't just a thing you can do in principle, it's a thing you can do in practice. You can find sort of very nice closed formulas for the correlation functions and even extract asymptotics from this formulas. And I really have no idea who to attribute here because it's so many people. This is a big area of random tiling theory, overlapping heavily with random matrix theory, probability, integrable systems. It's sort of core topic in the area. Probably like half the people here have done something like this, I'm sure, in a conference such as this one. Anyway, what do I want you to take away from this? The single dimer model is very well understood. Like, it falls into the class of models that we understand so well we can almost know everything we want to know about it. I don't think, unless something has developed since the last time I looked into this, I don't think that's the case for this SL2C double dimer model, and I can maybe give you some indication why. So let me tell you what the data of this model is. So this is going to be the target of the squish map, the sort of thing that the squish map produces. So what we're going to have, so again, we need a graph that's planar and bipartite. And each edge is going to get 2 pieces of data now. It's going to get a weight, so the complex number on each edge, right? And then there's also going to be a connection where we borrow the jargon from differential geometry. This is a 2 by 2 matrix with determinant 1. So each edge has got these two things, a weight and a 2 by 2 matrix of determinant 1. If you've got one of these double dimer configurations, again, so you should imagine here, some sort of, there's some doubled edges, there's some loops, maybe they're nested, it's some kind of pretty complicated situation. So what's the probability? It's going to be 1 over the partition function times the weight of the configuration. Abusing the word weight, I guess I've used it twice. So what's the measure of the configuration not normalized? Well, just as before, you take the product of the edges, the edge weights. This is exactly the same as in the single dimer model. But then there is another term that's the contribution of these 2 by 2 matrices. The 2 by 2 matrices don't see the doubled edges, they just see the loops. And what you need to do is you need to take the product of all of the 2 by 2 matrices around each of these loops. This gives you a matrix for each loop, and then you take the trace. It's not completely clear that this is well-defined, but then when you think about it, it is completely clear that this is well-defined, right? Trace is like cyclically commutative, so it doesn't matter where on the loop you start when you're multiplying your matrices together. And then there's, I guess, some question of which way around you go. Well, you could just sort of decide that based on the orientation of the plane, but also, that also kind of doesn't matter because these matrices have determinant 1. So, and then Z, that's just, that's the thing that you want to compute with like some kind of Castellan matrix, right? That's just the sum of all of these contributions over all double dimer configurations. So, well, how do you do it? So Rick writes down this matrix, again, called K for Castellan. Maybe you want to think about it as a certain matrix whose entries are in SL2. So this is a matrix with, over some non-commutative kind of ring, right? And it's not even like completely clear that determinant has any nice properties over such rings like that. But in this case, well, the fact that these matrices are all determinant 1, what you do, you can still make sense of this Laplace expansion for the determinant, right? When you take the determinant, it's a sum over permutations. You can take those permutations and break them into disjoint cycles. And so what you do is you've got all these 2 by 2 matrices. You take products of all of the 2 by 2 matrices around the different disjoint cycles in the permutations that are coming from the Laplace expansion. And then for each one, you take the trace and multiply them all together. So there's a notion of determinant, it's called like quaternion determinant or something, QDET, right? It's sort of well behaved. But I don't think it's well enough behaved that you can extract any information about the correlation functions. And again, if I'm out of date on that, please let me know. But based on some out of date information that I have, I don't think this trick with K inverse works. Kramer's rule just sort of fails over rings like this that are so badly non-commutative. So if you want to access correlation functions in this more complicated double dimer model, you have to do something else. And our idea was, well, let's see how much of this model is made up of actually just the single dimer model that's been squished there under the squish map. And I can take whatever information I know about correlations in the single dimer model and just push it through to the double dimer model and then learn what I learn. So that's the motivation. Using the squish map to learn something about the correlations. And again, for this audience, there's a pretty good analogy here. Maybe you know about 6 vertex model, right? This is a model which is exactly solvable in the statistical mechanical sense in that you can compute its partition function by taking some determinant. But it's not one of these Castellan type or Gesell-Vienot type determinants or things like this. It is this Isergen-Korpin determinant. The reason we know that this determinant works is essentially by something like computing the Vandermonde matrix, right? It's that kind of computation. I don't personally know interpretation of minors of this. I guess Paul is here, so he could tell me what interpretation is if it's there. But on the other hand, there is all of these different parameters that you can have in the 6-vertex model. And there's this one particular nice choice of parameters called 2 enumeration. And it was realized indeed due to that. So the alternating sign matrix question is 1 enumeration, essentially. And the 2 enumeration, basically, thinking about this question is where people realized that you should study the perfect matchings on the Aztec diamond. This is the observation of Elkish, Cooperberg, Larson, and Prop from the 90s. So this is like probably the best or maybe second best instance of the dimer model to study at all. Everything is known about it. So there's this one beautiful little line through the parameter space of the 6-vertex model called the free fermion line, where we know everything. We know the correlation functions and so forth, basically by way of the Castellan theory or one of these other equivalent things, the Gesell-Vienot, inert beta type stuff. That is the hope for finding the one part of the SL2 double dimer model that we can actually understand, because it's secretly just the single dimer model. That's the idea that we want to do here. This is why we're trying to embed the single dimer model in there. So let me tell you the idea of the proof of our theorem here, that the squish map hits the SL2C double dimer model at all. So let's think about these specific weights on the single dimer model for now. These edges get weight A and A inverse for some A, B and B inverse, C and C inverse thusly. I think you'll see why I want to do these ones in particular in a bit. But it's kind of like the first one, which is interesting. Of course, we could do uniform measure, but then it's not clear what we've done. It's always kind of sort of unsatisfying to say, here's a problem that I've solved, and then here's just like a really bad way to interpret it. That's sort of not so motivating, but this is a good set of weights. It's gonna squish to something interesting. Yes.
What about the little edges?
They get weight 1.
Okay.
Sorry, I should have written that, but that's too many ones to write on the picture. Yeah. We call these propellers, sort of for obvious reason. They're the thing that squishes down to give you just a vertex. I can now answer Arvin's question from before. Why do you get degree 2 everywhere? It's kind of brute force, like what, at each one of these propellers, right. At each one of these propellers, right, like one of these edges is going to be there. Why did it do that? Wait, no. Can we just be a highlighter? Like, no, I guess we can't. Okay, fine. On each one of these propellers, one of the edges is going to be there. Keep ink. And then what else can happen? So the other 2 edges, the other 2 vertices in the propeller have to be hooked up somewhere. So if I just look at the propeller as a whole, the separate vertex there is good. That edge, the short edge, is going to be of not interest, and what I just see is degree 2. So that part happens for sort of easy reasons. Undo. Don't want any of that. Okay. So what I want to do is I want to define these 2 matrices, L and R, and then I also want to define these diagonal matrices, A, B, and C. And then we are going to use those matrices to do computations in the single dimer model. And they're not going to be like the fancy matrices that went in the determinant. This is going to be normal transfer matrix technique for computation in the single dimer model. Here's what I mean. So I've got this configuration. It's going to squish down to some double dimer configuration. Fix that, and let's compute the weight of everybody who squishes there, right? Just like the whole fiber above this one double dimer configuration that I fix. So we're going to do that loop by loop. So given a loop, what I do is, do I have this written down? Oh, I guess I just said it. So if I'm doing, like, for instance, the boundary of a single hexagon, right? To trace out a single hexagon, I see an edge that's weight A, and then I turn left, and I see one that's weight I guess, B inverse. I think I maybe chose a different convention than what was in the paper, just randomly because of me, I guess. And then I turn left again, and then I see an edge that's got some C's on it. And then I turn left again. So I just go around turning left 6 times. I get back where I start, and I pick edges up A, B, C, like that. And so I'm going to make the corresponding matrix product. A, turn left, B, turn left, C, turn left. The inverse or not, that depends on which direction I walk down the edge. So if I walk down the edge like this, I pick up an A. If I walk down the edge like this, I pick up A inverse. So I take this matrix product, I take the trace. Yeah, Sanjay. Oh, yeah. The A, B, and C, they're diagonal matrices with weight little a is parameter.
Where do you attach the L and the R? To which edge do you attach?
L and R attached to vertices, and A, B, and C attached to edges. So we're not at the SL2 double dimer model yet. Okay, any other questions? Yeah. Yeah, so here I basically just wrote it down what I just said. So we're going to traverse the loop counterclockwise and write down this prescription exactly, A or A inverse, et cetera, and then L or R when I turn left and right. And then the observation here is that L is actually the transfer matrix for turning left. So you could imagine like writing down a vector that's going to tally up the contribution so far from traversing the loop. If I had this edge, I'm going to start with a vector with weight 1 there. If I do that and I turn left, then this is the only thing that can happen. I have this, I can't have this edge here because then that would be double covered by, right, so only that lower edge is possible in that situation, and so the output for this input is 0, 1. On the other hand, if my input is 0, 1, both of these configurations are possible, both this blue one that I've written here and the black one. Either one of those is allowed, and so either one of these edges is allowed to be there. So this is the thing that I get as well. So you can imagine just taking this product of matrices and just iteratively multiplying it on to tally up the whole contribution as I walk around the loop. Maybe it looks something like x naught x1 at some point after you picked up some stuff. After doing that left turn, it should now look like x naught plus x1. X1. Did I do my matrix multiplication correctly? No, I totally failed. X1, X1. No, we gotta, yeah. I am a mathematician. Wait, what was this supposed to be? You got X1 and then X naught plus X1. Fantastic, yeah, and I failed it. But I passed the revision. Okay, right, and then at the end I take the trace. That's like saying that whatever configuration I started at, maybe I want there to be an edge there. I also have to end with an edge there. I can't start with an edge there and then have the other thing. So that's why you need to take the trace. Does that make sense? This is our like kind of standard method in transfer matrix theory if you just want to understand the contribution in a stack mech model, iteratively like this. You can check that matrix L, if I raise it to the 6th power and take the trace, I get the number 18. That is the same 18 as before, right? These are the 18 configurations that give me this single hexagon. That is the same as setting A, B, and C all to be 1, so just not keeping track of those parameters. If you do keep track of the parameters, you get a mess with 18 terms in the mess. There's all sorts of other loops. They're even worse to write down. So the point is to think about doing this conceptually, right? Not to actually do it. Although Leigh did a massive amount of computational work actually doing it just to make sure that everything was working. So essentially, basically following up on Sanjay's question is we want to move those L and R matrices onto the edges. Right now they're associated with the vertices of the graph. If I have these 2x2 matrices of all determinant 1 on the edges, then I win. I've basically got this SL2C double dimer model. So I should just tell you the prescription. It's the amount of work which went into working out the details for how to do this was just sort of so many 2x2 matrices, messing around with them for months. That's the method, and that's also kind of the proof. But right, so you take this matrix, it's a diagonal matrix with a -1 in the corner there, and you set alpha to be I, it's I, right? The imaginary diagonal matrix with I times A and times J. Both this matrix and J have determinant -1, so this whole thing actually does have determinant 1. Right. Similarly, you set beta to be this particular product of the R and L matrices. Again, I think I have B inverted from the way it is in the paper. I'm sorry about that, as I was being careless. And then gamma is just this particular product of these matrices. And then you write all of the alphas on an edge of this direction, all the betas there, all the gammas there. The reason I wanted to use this particular weight function actually is just so that it's easy to make the slide. Then I can say what to put in the A edges, what to put in the B and the C. So those are the connection for the SL2C double dimer model, those alpha, beta, and gamma. So for instance, let's just check it. There's a lot of things to check, but let's check the easy one where it's sort of clear what's going on. Say I've got some, I'm doing Kenyon's determinant. I've written down a product of these things inside a trace, and I want to know what happens when I've got some stuff, and then an alpha, and then a beta. Right, so I write down the prescription for what the alpha and the beta is, according to my rules. And then, right, so I is indeed a scalar matrix, so I can just pull it out, and it becomes this minus sign out here. I don't need to worry about it. J actually commutes, it doesn't commute with the left and right matrices, but it does commute with A. A is diagonal, right? So this I can pull out here. I get J squared. J is idempotent, so this is gone, and I just get B left A. That's the sort of thing that I said that I would have in my first prescription when I was doing the transfer matrix computation. I pick up a weight from matrix A, I turn left, I pick up a what's that? Oh, the R goes with the next term. Like so I think I dropped an inverse, or maybe I don't know. Possibly B got inverted, I'm not sure. I have to fix that in post. The overall sign, indeed, also dies because these paths are even length. Right, this is a path on a bipartite graph. So that is how it works. So it's not really a proof. The proof is like you check these 12 identities and it works, which is kind of a bummer, but proofs go like that sometimes. Let me say loosely why it works. L there's not really very much nice about L at all, right? If I raise it to the 6th power and take its trace, I got 18, right? We asked for that. On the other hand, if I put this matrix J on there, I get this matrix. And this thing is order 6. Indeed, even better, it's almost got order 3. Like if I cube it, I get minus the identity matrix. So up to some signs that I don't care about, this says turn left 3 times and you get back to where you started. Right? That's what you do on the hexagon graph because these are all trivalent graphs with angle 120 degrees. That is, 2 lefts is more or less 1 right, up to some signs and up to putting this tweak in the matrix. The proof that we do basically amounts to telescoping all of the tweaks in this sort of intricate way. Yeah, it's one of these, I just think this is beautiful. Like having found it, Leigh having found it, I just get to look at it and say, I can't believe, like, who asked for this? It's one of these things that you feel is, you discover rather than engineer. I'm normally used to just hitting a problem with my computer until it dies, but this really feels like there was something to dig out.
Until the problem dies or the computer?
My computer is 10 years old and it's still kicking. Not this one. This is some Windows tablet. I have a very contentious relationship with it. Okay, so let's figure out. So with this particular collection of weights, what do we get? So we got this very interesting connection. The connection, again, this jargon from differential geometry, that means the matrices, yeah? So the weight function we wound up with was trivial. Kenyon's SL2C double dimer model is allowed to have a weight function in addition to the connection. We didn't use it. So you can, right? If your single dimer thing is, still two periodic, but you had a different weight function, just a different two periodic weight function. Well, kind of divide out the stuff that isn't the weight function I showed you before, right? Take my weight function, write it as a part that's going to squish plus some extra stuff times some extra stuff, because these are multiplicative weights. Just arrange for the extra stuff to have the same weight on any two edges that are going to squish to each other, and arrange for the squish stuff to have a complex number and its inverse on any two edges that squish together. There's a unique way to do this kind of splitting. And then having done that, this part becomes the connection, and then this part becomes the weight function on the SL2C double dimer model that I didn't use. So it does always work as long as I have. If I don't have something, we didn't say it in the paper, but it's kind of clear. If I don't even have a periodic weight function on the single dimer model, do the same thing. It's just you don't get the same matrix A on every edge. You get a different matrix A on every edge. But it's fine. So that's what you should expect if your model isn't periodic. So why did we notice this? So this is the part, the noticing part is the one thing that I did a long time ago. So for my PhD thesis, I was studying this particular weight function on plane partitions. It's kind of like three-dimensional checkerboard. Boxes in the corner get weight Q. And then, so here I've drawn the weight in the middle of the cells. So if you put a box there, then it gets weight Q. That's the origin. Here's the point that's one out on the x-axis. If I put a box there, it gets weight R. And then if I put another box out on the x-axis, it gets weight Q again. So there's this very particular two-periodic weight function on plane partitions. In general, you probably shouldn't just try to write these things down and then compute generating functions, because it's going to be terrible. Plane partition counting is hard. In this case, here's the empty plane partition. There's the one with one box in it at the origin. These are the three dominoes, 1, 2, 3. And they get weight QR, QS, and QT. Here are the 6 things of weight 3. QRS is like this L-shaped plane partition here with 3 boxes on the ground, etc. These are the ones that have got a triomino out one of the axes. Right? So you have that mess. The thesis, my thesis, not Leigh's thesis. So you make some notation. So let's use capital Q to be the product of these 4 variables that I set up before. This is basically McMahon's generating function for plane partitions with a perturbation out front, like it's like Stanley's trace generating function or something. M twiddle is just M times M with the first parameter inverted. That's just all written down so that I can fit the next formula on one slide. So the next formula is the generating function for plane partitions with this very particular weight is this mess. I mean, it's a mess only in that it's a big function, but as far as formulas with 4 variables in it, this is kind of as nice as you could possibly want, right? It's a product formula. It's got all of the nice features. My thesis was proving this fact. It was just something coming from algebraic geometry in just this very particular way that's out of scope for this talk, and in fact, probably out of scope for my research program also. But the claim is that due to this 2 periodicity, this thing now has an interpretation that doesn't have to do with any of that algebraic geometry that's out of scope. It's just a partition function for the SL2C double dimer model. Now, there's not too many of these partition functions known, basically because it's very hard to compute these Q debts, these quaternion determinants. So let's think about this formula for a sec. I don't want to take you through my whole PhD defense, but I want to tell you a couple of things about my formula. If I put all the parameters to be the same, that's like forgetting all the coloration in the checkerboard. So this is just going to recover McMahon's generating function for plane partitions. You can do something a little bit less brutal if you put if you set some of the variables equal. So the Q equals T and R equals S. So this is like forgetting the checkerboard striations out in the Z direction, right? So this is like just a regular, ordinary checkerboard now on the floor. And there's a 2-variable generating function. It counts plane partitions. There's a big simplification that happens, a whole bunch of terms in the quotient die, and you see that you get just 4 McMahon functions. 2 copies of M1, well, QR, capital Q if you like, and then M tilde of R. Yeah, so one with an R and one with an R inverse. So this is actually way easier to prove than the thing I proved. You can do it with Schur process techniques, for instance, like vertex operators. Indeed, the thing that I did with vertex operators, I mean, my theorem came from vertex operators as well, but it was kind of horrible. Like the things that you do with Schur process that make it so great for extracting asymptotics, none of them work on my formula as far as I know. So this thing is considerably nicer. So another thing you could note from this formula, this was the original motivation for thinking about this squish map. If you put the extra variables to be -1, then actually stuff just cancels out of the numerator and denominator in the obvious way. The only thing that doesn't cancel is 2 copies of the McMahon function. So this suggests that if you put actually a negative, this is not a combinatorial thing to do, but if you put like a -1 on some of those edges, you should see 2 independent plane partitions popping out. So this is what the squish map is doing. It is actually just giving you, this is the instance in which the squish map hits a trivial SL2C double dimer model without any interesting connection. And the new content is what happens in not that case. So one thing that doesn't happen is I don't get a new independent proof of the result of my thesis. That would have been too nice. Maybe if we're really good at computing Q depths, then I can just take some determinant and my thesis will fall out of it. But I don't think that's going to happen. Leigh is doing a poster later today, and she's going to talk about a different specialization in which instead of putting R, S, and T to be -1, you put them to be a particular root of unity. And when that happens, a really neat thing happens. You get this sort of tiling problem that sort of relates back to Conway's tiling groups, tilings with stones and bones and things. So that's very neat. So look for that poster. Future things. So these are probably joint with Leigh and Megan Bose, who's a current PhD student at University of Oregon. So one thing we could try and do, you could try and squish a graph like this with the idea of maybe hitting more of the SL2C double dimer model. Let me say that this map doesn't cover the entire parameter space of the SL2C double dimer model. There's only certain things that it will hit. But so what if you start with more places to put weights on the edges, right? Can you get more fancier matrices? The answer seems to be no. Bose does this calculation, Megan Bose, that if you have a thing like this with weights A, B, C, and D on those cross edges, then one of B and C has to be 0. You wind up requiring that AD minus BC equals 1, and somehow also requiring that AD plus BC equals 1, and that's kind of a bummer. Like you can't have both things at the same time. Can you squish other graphs with degree other than 3? And again, clever answer of Megan's is maybe. If you kind of stitch in 2 propellers at the vertices, it looks like maybe that'll give you something, but then we don't quite know what to do next because we haven't really looked at it. See also my academic brother, Neil Cheetah, and my postdoc mentor, Kurt Johansson and Vincent Beffera. I think it's this paper where they were doing another thing that's like a squish map on the square lattice, but they put something entirely different at the vertices. Lastly, is there a boxed plane partition variant of that thesis generating function? I would really like this. This maybe would allow us to start, inverting Castellan matrices and just actually computing correlations anyway. Not that we know, though. Shuhei Kamioka has this. He claims that he's got a formula that generalizes this for box plane partitions. If you're here and you understand anything about this or the mechanisms that make it work, namely the discrete Toda hierarchy, please come and talk to me and Leigh before I leave. We've worked quite hard to try and understand how to use Kamioka's work for this purpose, but we were not able to make any headway. So yeah, if you know discrete Toda, please come and talk to us. We'd like to talk to you. And that's all. Thank you very much. I'm sorry I was late.